Special right triangles are going to be an essential part for us whenever we're talking about trig. A lot of the things we're going to do without a calculator when it comes down to evaluating trig functions are going to require us to reflect upon special right triangles. We have two special right triangles. We have the 30, 60, 90, and we have a 45, 45, 90. Sometimes they might give you a side relationship or an angle measurement. Sometimes they might give you the congruency symbols. Either way, that's one of the ways that you can actually recognize it. As far as the relationship goes, in a 30, 60, 90, the relationship goes 1, 2, square root of 3. Meaning that if we know the small leg, or the side opposite the 30-degree angle, the hypotenuse is twice that size, and the long leg is square root of 3 times that side. Kind of a weird number, but it's that proportion that makes it easy to calculate. We can go forward or backward sometimes, and what I mean by that is, essentially the short leg is the key value to actually find. But if they give us the hypotenuse, if we divide it by 2, that takes us to that value of 1. I'll model that here in a moment when we talk about some of these special right triangle problems. The relationship for 45, 45, 90 goes 1, 1, square root of 2. So again, you can see this 1 value. That's an essential value for us to actually find. So if we know the leg, we just multiply by the square root of 2 to get the hypotenuse. If we know the hypotenuse, we divide by the square root of 2 to find the leg. Let's take a look at a couple examples. All right, in our first set of examples, what we're dealing with here are all 30, 60, 90 right triangles. Best case scenario is our first example here. You can see we know the short leg opposite the 30. So right off the bat, I can get the hypotenuse by multiplying it by 2. Because again, that's our relationship that was discussed up here. 1 to 2 relationship. So I just multiply that by 2. To get the long leg, multiply by the square root of 3. Now, second best scenario, they don't give us the short leg, but they give us the hypotenuse. So if I have the hypotenuse, I just cut it in half to find the short leg. Once I know the short leg, I multiply it by the square root of 3 to find the long leg. And then finally, pretty much the hardest situation is if they give us the long leg. So if they give us the long leg, we still want to find that short leg first. And how we're going to do that is just take the long leg divided by the square root of 3. So again, if I were going in this direction, I would multiply. So if I know the short leg, I multiply to get the long leg. However, if I know the long leg, I'm going to divide to find the short leg. I'm not done yet, but I have my essential value, and I'm just going to double that to find my hypotenuse. Sometimes if you check in the back of the book, you might have to rationalize those answers, but for our sakes, we're going to allow to have radicals in the denominator, so that way we can see our side relationships pretty clearly. Let's go down and look at then the 45, 45, 90 is a little bit easier for us. We have two situations in this, and keep in mind, our side relationship for a 45, 45, 90, this is 45, 45, 90, is 1, 1, square root of 2. So in a similar fashion, if I know a leg, well, obviously I know the other leg because they have to match. And then to get the hypotenuse, I just multiply by the square root of 2. But on the flip side, if I know the hypotenuse, to get a leg, I have to divide by the square root of 2. So again, as I alluded to in the previous question, we would be all right leaving a radical in the bottom, but if you wanted to rationalize this, you multiply by square root of 2 over square root of 2, which would give us 10 square root of 2 over 2, which is 5 square root of 2. Which again kind of makes sense, because if I think about taking 5 square root of 2 times the square root of 2, the square root of 2 and square root of 2 becomes 2. 2 times 5 gives us our 10. There we have special right triangles.